there's nothing to write down here. It's just a different form from what you're used to. Okay, so they define this as the delta x over, or sorry, delta y over delta x. The limit as delta x approaches 0. And if you relate back to the picture that I had, this will make sense. How did we generate that delta y? Well, that delta y was the top value minus the bottom value. And remember, the two y values we had were f of x plus delta x and f of x, which gets us to this thing. Now, the only difference here is instead of using x's, they use c's, because now they start talking about a specific point. And again, we talked about this terminology here. Instead of x comma y, we're doing x comma f of x or c comma f of c. Not a very exciting thing. But we do have this to talk about. We get, occasionally in a graph, we will get a vertical, hold on, let me get to what I'm talking about here. There we go. We're getting a vertical tangent. Okay, so a vertical tangent is going to come about on a function where that, like the parabola, we start talking about that slope getting bigger and bigger and bigger, or smaller and smaller and smaller. In other words, approaching infinity or negative infinity. When that happens, we get something called a vertical tangent line. And I'll show you what that looks like. The next slide has a picture here. But this is where you're going to get it. If the limit of that function, or the limit of that difference quotient, goes to infinity or negative infinity, then we start to generate a vertical tangent. And the function can be continuous there. And in fact, my example in the next slide is continuous. But the slope of the tangent line does some funky stuff. So the example of that would be something like this. That function is continuous. And if you think about that tangent line sliding along the curve, start down here at 0. As it starts to slide up, it's getting bigger and bigger and bigger, approaching infinity to that vertical line. And then coming from this direction, also doing the same thing, approaching a very large value.
So is it not approaching negative infinity as well?
It can, yes. Doesn't have to, though.
Well, so it basically depends on what side you're coming from, right?
Correct.
Okay, so if you were to come from like the top and then shift it down, it would be approaching negative, right? From the right side?
No, because it's getting more and more positive as you move over. Right? This is a 0 slope,
Oh, okay.
and now it's positive and goes down to positive infinity.
From the other side, it's getting also more positive.
Also more positive, so it's infinity, infinity. Okay. And what's going to happen is we'll see examples in the future. I don't think we'll cover it today, but we'll see some examples where one side goes to infinity and one side goes to negative infinity. That gives you a different monster. For now, we're just concerned about a vertical tangent, which is if they both go to infinity or they both go to negative infinity. And again, not contingent on it being a continuous function. And now things get a little bit more difficult because we talk about continuity. So a function is continuous or discontinuous. But now we also have to talk about differentiable versus non-differentiable, meaning can you take the derivative? But we have to talk about terminology first. So how do we equate this limit process thing that we did, where we use that calculation to get the slope of the tangent line to the curve at a certain point, or in general? And now we start bringing calculus into this, because really, we didn't do a lot of calculus when we did that x squared example we just worked through. It's pretty much algebra. Plug and chug, take a limit. Yeah, you could argue limit is a calculus concept, but still not that difficult. But now we want to start relating it to calculus terms. So we have this thing called the derivative. And the confusing thing is, and I'll explain why in a second, there's a whole bunch of different notation, but the most common is we're going to go with that, which is, you see that little apostrophe in there. Okay, that's read as f prime. So f prime of x, also known as the derivative of x, is equal to that formula we've been using for the last couple days. And that gives you a derivative. The process of finding a derivative is called differentiation. If you can find the derivative, it's differentiable. All this weird terminology going on that all says the same thing. Can you or can you not take a derivative?
So if you can, it's the differential equation.
if you can, it's differentiable. It's not a differential equation, that's something different.
That's something else. Oh.
Yeah, we'll get to those later. Yeah. And in fact, if you go into some branches of science or math, there's an entire course on differential equations. It's fun.
I'm sure. It's just a party.
What's that?
It's just a party.
Oh, yeah, yeah, yeah. Okay, so a whole bunch of different notation. They all say the same thing, just different ways of writing it. So you're asking yourself, why are we doing this? Why do we have all these different names or notations for the exact same thing? I'll explain that in a second. This is the most common that we'll use, f prime of x, or g prime of x, or h prime of x, whatever you want. This one is also fairly common, dy dx. That means the derivative of the function y with respect to the variable x. Most of the time, that's the type of derivatives we're going to go into, but if you go further into math, you'll see that you can, well, not even, we'll talk about it in this class too. We'll take derivatives with respect to other things. Like, for instance, we'll be doing some word problems involving, I don't know, filling a pool. And so if you're filling a pool, you stick a garden hose in the pool and you got to you want to go out to lunch, but you got to calculate how soon till the pool's overflowing. You don't want to be away when the pool starts to overflow, so you do some calculus in your backyard, which I'm sure we all do on a regular basis. We might be calculating something like dv dt, which would be the derivative of the volume with respect to time. So these can change, but in general, when we're starting, dy dx, derivative of y with respect to x. Then we can throw in a y prime there. What is y prime? That's the derivative of the function y. So instead of changing the y into an f of x, we use that. Then you got this guy. Instead of just calling it y, let's change the y into an f of x. All of these make somewhat of pretty good sense, and then you throw that weirdo in there, which is the capital D derivative of y, and then the lowercase x means with respect to x. Si, senor.
So I get derivative, where you get it, what we were just doing, but what does it mean, derivative of y with respect to x?
That means your function is y, and your variable is x.
Oh,
We will see problems later where you'll have multiple, there's a thing called multivariable calculus, where you've got a whole bunch of different variables and you need to know which one is your variable and which one are constants. That's going to be fun. Yeah, we can touch on that a little bit, but it won't kill anybody. Okay, so blah, 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 and then all the different things we talked about. So it's just notation stuff, okay? All right, so now let's talk about these two chuckleheads. Isaac Newton. Everybody know Isaac Newton? What's he famous for?
Inventing calculus.
Inventing calculus.
Inventing
apples.
Where else have you heard him?
Inventing apples.
Inventing apples?
Yeah, something with that.
Right, what, do you know the story about the apple thing? He got hit on the head with an apple and,
After surviving the plague.
yeah,
I
and
think it was
discovered,
during the plague that he did
discovered gravity or did
The
some stuff,
gravitational constant
yeah,
or
Newton's,
something like
yeah,
that.
all that fun stuff. Then you got this guy. It's a little hard to see, but he's got some quality hair going on
He's
there.
got some, that's the guy on our
That's
course.
right, that's Leibniz. So sad story. I know, I'm sorry, I started on a sad story on Monday. So everybody knows Isaac Newton, no one knows Leibniz. This is how supposedly the story went down. So both of these guys invented calculus at the same time. And that's why we have different notation, because Newton was working with one form of notation, Leibniz was working with the other form of notation. So way back when, Isaac Newton was like a rock star. For some reason, mathematicians were cool. Like walk down the street, people would ask him for his autograph, that kind of stuff. Yeah.
The chicks dug Isaac Newton.
He was also in charge of some international math group. So he was the chairman of some international math and science group. So he was very well known. He's out there raking in the dough. He's on speaking tours. He's telling everybody about this calculus thing. And then this guy Leibniz pops up out of nowhere. And he says, oh wait, I did the same thing. And so people start asking the question, how is that possible? How do two people that have never met each other come up with the same mathematical ideas? Could be. But Newton gets a little pissed. This guy's cutting into his time with the chicks. So he goes after him and ruins his life. So Newton
That's so
gets
funny.
all his math buddies together, and they just start making Leibniz's life you know, just a living hell. You know, they're calling his cell phone all the time and hanging up. You know, calling off for telling him he won a trip, you know, a free cruise. You know, he's getting all these spam emails. They're signing him up for all these magazine subscriptions and all these websites. So he's getting like,
Spam up the wazoo.
yeah, Walmart emails all the. They're just driving the guy insane, and it works. So Newton ends up ruining Leibniz's life. Newton dies famous. Everybody knows about his laws of gravity, and he was the head of this, and makes a bunch of money. Very famous. La la la. This guy dies alone and broke. Even though he did, yeah,
Where's he from? Like,
this guy I think is.
It doesn't matter.
I think he's might be Austrian or German or something like that. I don't know.
And like it's other.
Yeah, Leibniz is like German, I think.
It's like Germanish, but it's more. It's like not quite. Like it's different. Like back then.
Are you a language or a name specialist or something?
No,
Is that a
I just know
hobby
a
of
lot
yours?
I know a lot of Germans.
All right. Now, why do we have the different notation? Because Newton worked in one notation and Leibniz worked in the other, and because they can't really narrow down who actually invented calculus, we've stayed with both notations over time. Okay, Newton, I believe, was the f prime of x. Leibniz was the dy dx. It doesn't matter because we'll play with both of them.
What's your favorite?
I like the f prime of x, but that's just me. Personal preference.
What do you like more between them?
Leibniz. I like to vote for the underdog. Newton was a bully.
what did he actually do to ruin his life?
Did it kill some people?
Just what I described. I mean, he got all,
He
he,
expanded.
yeah, and got his math buddies together. He talked about how he stole his calculus ideas. He accused him of plagiarism,
Oh, okay.
even though he's like, what are you talking about? I live in.
I've never seen you before.
Yeah. Who are you?
Who are you, Apple, dude? You got some brain damage?
Yeah, exactly. I think you got hit on the head a couple too many times. Okay, so all I'm asking is, well, let me ask you. What am I asking in that problem?
Is
What should you do? And don't tell me take the derivative. How do you find the derivative?
Good question.
Hence the reason I asked it.
These are gonna take long.
Mm-hmm. I notice you haven't answered my question.
Why?
Sydney,
I'm just gonna
The
take
difference-
that.
take a shot at it. Go ahead. What's the worst that can happen? You're wrong and your brain grows.
Yeah, well, to use like the, what is it, the difference equation?
Yeah. Good.
Right?
Yeah. Also known as the limit process.
Limit.
All right, so we're not going to do this one because it gets a little nasty. So let's just set it up.
Okay, it's got
You want to go, Sid, or?
okay, so then it's x plus the change of x cubed, parentheses, cubed, then plus 2, oh no, then it's minus,
No.
right? Yeah, plus, yeah, so 2x.
Somebody help her out.
X plus delta x. Minus.
Okay, you understand where that came from?
Yeah.
Okay,
There it is.
keep going.
Okay. Minus, is it x cubed plus 2x? Parentheses,
There you go. Good.
all over,
Sorry.
delta x.
Good, good, good. Okay.
Good find.
So you can see what happens here. We have to cube x plus delta x. You know how to do that?
Yeah.
Mm,
What would you
A
use?
plus B.
Oh.
I'm sorry? No, that's if you factor it.
Just
Yeah, you could use Pascal's triangle, or you could just do x plus delta x times x plus delta x. And then take that answer and multiply it by, yeah, whatever, I don't care. That's why we're not gonna finish this, because it gets a little nasty. But still doable. And again, if you've done it correctly, when you're done, or, sorry, not when you're done, but as you're starting to solve this problem, you should get things dropping out properly. Because remember, our ultimate goal here is to get that out of the bottom. And why do we want to get the delta x out of the bottom?
Because then when
Cam?
It'll be undefined.
I'm sorry, what?
It'll be undefined.
Correct. Our last step here is to take the limit as delta x approaches 0. With this in the bottom, we can't do that. So if this is going to work, you have to get rid of all the things that just have x, factor out a delta x, and cancel, and you'll see that pattern continues to repeat itself over and over again when solving these problems. If the delta x's don't cancel, you've probably made a mistake. And then you get down to the bottom, and after you work all that fun stuff out, you get 3x squared plus 2. I did a lot of math magic there to get that answer. Okay, but if you got nothing to do this afternoon at lunch and you're just sitting there and you want something to do and you want to finish that problem, you should get 3x squared plus 2. Question?
So when you look at like the original equation, what are going to be some like tellers that it's not going to be differentiable?
Oh, good question. We'll get there.
Okay. And then also for the last one, since it was x squared and the answer was 2x, which is like, so if you take the x and then put the
Save
2,
that for later.
yeah, because there's a
Yeah,
little- some
yeah.
relation.
Okay. Absolute value graph. This will be something that'll pop up frequently to take a derivative. The problem is, if you plug x plus delta x into the absolute value graph, or into the absolute value function, you can see that it gets a little bit ugly. So if I try to use the limit process for this, it's not going to work out so well. So we have to be a little bit sneakier. For instance, what is the derivative at 4? Did it scare you? All right, so let's think about this. What am I asking you? At the value of 4, so it's going to happen here, I want to know the slope of the tangent line to that curve. Curve.
The left.
I just.
1. Why?
Because it's a straight line.
It's a straight line, so the slope of that straight line would be 1. All right, what about if we take the derivative at 1? Negative 1. What about at 2? 0. Why?
Y
Because there is no slope.
So you think we'd have this? Touches in 1 point, right?
Yeah.
And that's what we want for a tangent. Hey, does that touch in 1 point?
Yeah.
Sure looks like it. Does that touch in 1 point?
Yeah.
Can it have 3 different slopes?
So
No.
at that point
One
it's
tangent line
infinite.
cannot.
No.
Because there's an infinite amount of
That point is undefined. We call that a corner. A graph with a corner. Corners are the first example of locations that are non-differentiable. We can't take the derivative at 2 for that graph. If you think about it graphically, I can put a whole bunch of different tangent lines through that point. And they have to have the same value, and since they won't have the same value, it's non-differentiable. But we'd also like to talk about the calculus that gets us that. And we get to this. You look at the one-side limits. We did that already. When you come from the right, when you come from the left first, you have a limit of -1. When you come from the right, we have a limit of 1. Now notice I'm taking the limit of the function. Okay? Or I should say the limit of the difference quotient. It's just a different form that you're not used to, but it's still the same thing. I'm taking that difference quotient and I'm taking the limit of it as I approach that value. They don't match. And therefore that point where they meet is going to be a corner, which is going to generate something that's non-differentiable. Yes.
What's like the basic equation you like to get to like that first one? Like what's the equation that you look at?
It's an alternate form of the derivative, which we haven't really talked about, which is f of x minus, well, here, I'll write it down. It doesn't pop up very often. F of x minus f of c over x minus c, and that's the limit as delta x approaches. Oh, sorry, as, there's no delta x there. As x approaches c. And the only reason I switch forms is because when you're dealing with the absolute value function, it's a little bit easier to work with. I should have considered that before I fired it up there. More frequently, what's going to happen is you're going to look at a graph, and you're going to be able to recognize a corner right away. Because a corner looks like a corner. Function does something like this. Let's suppose we have a piecewise function and it does that. Oh, look, there's a corner. But you can also think about it using that ruler idea that can I find that one particular slope there? The answer is no, so it goes out the window.
Is there, do derivatives work like limits where you can take like the numbers that approach that slope and, well, like a number that's 0.001 away, slopes don't work like that?
Correct. Because think about this. This has a slope of 0.
And it just totally changes, right? Yeah.
But that's a dot. Okay, now we get in, and let me get at this whole thing here. Okay, so this is kind of an important concept. Because I'm sure you recall, we've talked about this already, but I'm sure you recall your geometry logic unit. And we have this scenario. If a function is differentiable, then it must be continuous.
Is that just because the limit and the function are defined there, so it,
Yeah, think about the corner. Instead of a corner, you have a hole there. How do you take the derivative of something that doesn't exist?
you don't.
However, the reverse is not true. Just because a function is continuous doesn't mean it's differentiable. Like the absolute value function we just looked at. That function is continuous, but it generates a corner, so it's non-differentiable. Okay, and that's an important idea because we're going to see some theorems where you're going to have to discuss the idea of the continuity and or the differentiability of a function, and those two things are going to come into play. So again, differentiability implies continuous, but continuity does not imply differentiability. Good?
What were some of the geometry ones? If the converse.
Converse,
the inverse.
contrapositive, inverse.
The contrapositive of the inverse of the
Yeah.
converse is.
So if this is the original statement, this would be the converse. This is true, this is false. All golden retrievers are dogs, not all dogs are golden retrievers. We're done. Okay. Now I will tell you where we're going in the future. What's going to happen is, as you start working with this limit process, you'll start to realize it's a major pain in the butt. Okay? Some of them get a little nasty, and already if we looked at that x cubed function, if we would have multiplied that out, it would have been really hairy. So we're going to start coming up with some shortcuts, and that's what encompasses a majority of the rest of the stuff that we do, is coming up with new tools. Hey everybody, it's Mr. Mirandola.
Hi everyone. Yeah, go. You can clap it up for me. It's okay. Yeah. Go ahead. For a second.
Yeah, excuse me 1 second. Yeah, I heard. Okay, so anyways, where was I? Oh yeah, as we start to do the derivatives more and more, we're going to start to come up with more and more shortcuts and or tools to use to take derivatives, because certain things work and certain things don't work. And Cam's kind of already hinted that there might be some shortcuts. If you notice that we went from x squared to the derivative being 2x, or we went from the function 3x squared, no, what is it, x cubed, and got 3x squared. There are some shortcuts that exist, but we'll get to that after we understand this concept.